Hello everyone, good evening. So I'll be talking about how to build an image classification model using an CNN architecture. So before I go into detail of what is convolutional neural network, few minutes I'll talk about what is the computer vision, and then what are the different applications which can be applied for an image classification. And then I'll jump to the various layers in CNN architectures, and then how can we create a image classification model for a binary classification and multi-classifications. I'll walk you through with the Hanson Colab notebook file, which already have a couple of notebooks from my Git. So I'll be sharing you the notebook URL as well, so you can practice it offline. So post this section. So this will be more the objective of these sections. So computer vision, it is not a new. So basically, most of us we have been using in our day-to-day, in our life. For example, when I say like most of us, when you try to take a pictures, right, it is automatically try to detect the faces present in the focus of the camera, right? So most of us mobile phone comes with the inbuilt face detection algorithm, which is again a deep learning based model to put a bounding boxes around the faces, right? So, and the other examples which I can quote about, when you upload a photograph into the social media website, right? Like I can talk about Face ID, where automatically trying to tag the person's name, right? If there are persons' names which is not tagged, it will ask you to give a label for the particular person. Those images will be considered as a training data for the model. In near future, if you upload the similar person photographs, which can be considered for the inferences or to identify the person's name. So, and there are other examples which I can also quote. Like most of the matrimonial sites, they are trying to use computer vision based approaches to detect the fake profiles. For example, when someone is creating an profiles in the matrimonial sites, right? First, they will try to have a filtering mechanism, like identify whether the uploaded photo is a celebrity or not. Usually, celebrities will not create a profiles in the matrimonial, right? And then they will try to estimate the age of the persons from the photograph, and then they will try to compare from the descriptions of what the user has written. So these are some of the examples which I'm quoting for the how CV computer vision has been used many of the applications, and also I can talk about snapshot filters. Like for example, when you have a snapshot filters, right, it will try to show you emojis on top of our faces, right? For example, based on the emotions of the person, whether the person is happy or sad, there will be emojis based on the emotion expression classification it works. For example, to quote another example, if you have purchased specs in the Lenskart website, right? Nowadays, you don't necessarily to go into the in person to the store and then wear a specs, and then you feel know how the specs it looks, how it fit for the each of the persons, right? Nowadays, if you go to the website, they have a facial landmark points. It will try to detect the facial landmark points, and then they use augmented reality. Like whatever specs you choose, it will give you an output image with the augmented, the specs will be overlaid on top of the recorded faces, whatever input video you've given. There are a couple of other use cases. We can keep talking about it, but just to mention few of the application where the computer vision has been used. So what is meant by computer vision? So what is the difference between the human vision and the computer vision? So like when I say human vision, through our human eye, it captures, and then we have objects within the bowl, and then our brain as the knowledge pattern of all these objects. For example, whenever I meet someone new, right, we introduce each other, and then I capture the patterns or the unique person's pattern, and then I'll have the knowledge pattern of the particular person, and then I say the person X, Y, or Z, right? So the main part here, the human brain. So in terms of computer vision, the human brain will be replaced with the machines, and the camera will be replaced with the sensing devices. So I will be replaced with the sensing devices, and only the difference here, machine to perform some analytics on the video file or images, you need a two process. There will be a training and then inferencing part or the testing part. The training will happen on the offline process, where you will have a larger number of sample. You will give a larger number of sample for each of the unique objects which is present here, or which you want to perform a classification or categorize. And then you train a model based on the training data samples. The trained model, what we call as a knowledge patterns. Okay, so once you have the trained model, and then you use some unknown images or the unknown sample, model will be able to categorize what that object is present, or what that object belongs to. So but here we'll not have a concept called as a model training, but even like how the newborn babies, how we are trying to teach our babies to understand each of these objects, right? Similarly, we have to make our machines as a human brain, where we need a larger number of samples. Mostly the deep learning approaches are the data-driven approaches, where you need to provide a larger samples to train our model. Based on the trained model, we'll be able to categorize like based on our number of categories. So we have a two kind of classification problem. One will talk about binary classification. We say true or false. For example, a person or not, or a cat or not. So these are the binary classification problem. When I talk about multi-classification problem, when you have a more than one category or more than one classes in your data sample, in your data set, then we'll go for a multi-classification problem. For example, we'll talk about MNIST handwritten digit recognitions. So we have a handwritten digit between 0 to 9. So there are 10 different unique handwritten digits. So we call it a multi-classifications problem. Now let me go in detail of how we can build a model for the handwritten digit recognition. So in terms of computer vision, you can solve various problems. One of the problems are the image classifications. In this scenario, I have an object where my model is trying to categorize what are the objects which is present. So there are multiple categories are present, or multiple class labels are present, where my model is trying to predict bottle, cube, and cup. Okay, but in terms of classifications, one of the limitation is that it will give you what are the objects is present within the frame or within the images, but it does not give you what pixel region or the pixel coordinates the object is present. For example, you are trying, there are multiple persons are there. Okay, multiple objects are there. It does not give you which pixel coordinate is the cup, or which pixel coordinate is the cube, or X, Y, or Z. Okay? If you need the bounding box coordinates as well, we have the X mean, Y mean, and the X max, Y max. We call it the rectangular or the bounding box coordinate. If you want to know the each object, the pixel coordinates, then we go for an object detection or the localization problem. You will have additional information about the each of the object which is present in the images. Then we have a problem called of segmentation. We talk about semantic segmentation and instance segmentation. In terms of instance segmentation, when you refer object detections, right, when you put a bounding boxes for each of the object present in an images, you will see there are few pixels regions which is not a part of the objects, right? So what does the instance segmentation does? Like from the detected object, it is trying to generate a mask. It will only try to extract the exact pixel coordinate region of the object which is present. That is the beauty of the instance segmentation. Coming back to a semantic segmentation, it is a kind of a pixel level classification. Okay, what we'll do here, most of the architectures, we call it as a segment and the unit. Especially for the autonomous vehicles, many deep learning architectures related to semantic segmentation has been used. Like in terms of here, we'll at a pixel level, we'll try to do happen at the spatial domain across the all the matrix. But here we'll try to do a individual pixel level. We'll try to do a classification. If the prediction belongs to the background, then we have assigned as a like yellow color. Then there will be a mapping color value for each of the objects, and then it will try to assign a unique color value for each object. That what here it is visualized. But in terms of instance segmentation, doesn't bother about like whether it's a unique object, individual object. For example, there are three cubes are there. Each cube is assigned with a unique color. But here, in terms of semantic segmentation, we are trying to group the objects which belongs to a similar classes will be assigned with a unique color value. In terms of example to show you some examples. For example, we are trying to do a collision detections in the road scenario. Okay, we wanted to detect what are the vehicles in front of the moving vehicle. For example, here I'm trying to build a object detection model where it is trying to detect the traffic sign and the traffic light and the persons and the vehicles. So you will be able to detect at what distance the vehicle is present, so that we'll get an alert or the notifications when there's a possibility of collision. So there are a lot of applications you can work around with respect to the object detection. Just pointed out in terms of the road scenario, which can be a possible one of the use case. I'll pick it up the question and answering session at the end. Is that okay, right? So I'll spend my 10 minutes of my effort at the last 10 minutes. It's fine, right? And in terms of image, most of the computer vision image and video will talk about images, right? As a human being, how we perceive an images. The 8, for example, here, I have an image 8, which is represented. So how we perceive a human being. But in terms of machine representation of images will be a 2D matrices, okay? And here, the one which I have represented is a grayscale images. Usually it will be in color images where you will have 3 channel matrices. The depth will be 3. You will have a number of rows and the number of columns. We'll say the pixel resolution. Usually it will be like a matrix will be which will be a larger one. But here, to make you to understand, I've just given you a smaller matrix, which is 18 cross 18. If you look at here, the pixel 0 represent the black color and 255 represent the white color. Then we'll have a gray shades of values between 0 to 255. The one, the representation of image pixel coordinates, which belongs to digit 8, will be a foreground region. The other, the pixel coordinate, most of the pixel coordinate value which belongs to 0 will be a background pixels. Okay. At the end, how machine is going to perceive an images, it will be a numbers range between 0 to 255. So in this case, I have 18 cross 18. The total number of pixels will be a 324 pixels. Each pixels will be a one numerical value. So there are 324 numerical values which we can talk about. But if it is going to be in color images, then usually it will be for example, here I'm just representing so which will be a color channel images. But in terms of grayscale, the depth will be 1. But in terms of the color images, the depth will be 3. So assume I have a data set, binary classification data set, which I wanted to build a model. The use case here, the applications, digit 8 and the not digit 8. Okay. Whenever you are trying to build a model, make sure that the data samples, the diversity, we can say about the diversity of data sample, which is possible in your production environment or your test environment. Okay. If your data sample, if your training data sample is too biased towards a particular environment, and if your model is deployed in some other environment, it may not work well. So So when you do a data collection, for example, in this scenario where I'm trying to build a model to categorize whether the handwritten digit is a 8 or not, which is a binary. So 8 will be a true scenario and not 8 will be a negative scenario. So in this scenario, like uh, each person handwriting style will be different. Okay, and someone will be rotated style, someone will be a tilted position, will be a smaller one. So make sure your data samples covers all the scenario which is expected in a production environment. So try to collect your data sample. So in the true scenario, you will have a image sample which has only the digit 8, but in negative scenario, you will have other than digit 8 will be a negative scenario. So assume I have a thousands of sample images which has the digit 8, and thousands of sample images which belongs to a not digit 8. Okay, so now I'm going to build a deep neural network model which is going to perform binary classification of whether the given input image is a digit 8 or not. Okay, so now usually when I say a deep learning, we'll have a input layer and then the hidden layers and the output layer. Okay, so the input layer will consist of n number of nodes. So in this case, I have created a input nodes with the 324s. Okay, the shape of input layer shape will be 324. Since my input image dimensions will be 18 cross 18, which reshaped into one-dimensional vector of 324. Okay, so now this 324, each node will be a 1 pixel intensity value. There will be a 324 node. Each node will be a 1 pixel intensity value, which is going to be a input to the hidden layers. Okay, all these pixel intensity values hidden layers. So we'll have a multiple hidden layers to learn the classification.
Sorry to interrupt, but the voice is breaking a little bit.
To talk about too detail on this part. So I talked about how we represented images, and then talked about various layers in the deep neural network. So in terms of input layer, we'll have a number of nodes. So the number of nodes will be defined. The shape of input nodes will be defined based on the if it is going to be an image as an input for the deep neural network or the deep learning architectures. So I have a 18 cross 18, which is reshaped into 324 numbers. So I'm going to have a number of input layer nodes will be a 324. Each number will be a pixel intensity value, which is given as an input to the hidden layers. So here we will have a two hidden layers or three hidden layers.
Excuse me, sir. The problem is persisting. None of them can hear anything properly.
Either how many hidden layers I can have, that will once we have a hidden layers created, then we'll move on to output layer nodes. If it is going to be in binary classification, so we'll have a single node at the output layer where we'll get a probability score between 0 to 1, and then we'll put a threshold to categorize, we'll put a 0.5 probability score at negative scenario. So we'll get a probability score at the output layer nodes, and then we'll try to take a business logic no threshold to categorize whether it's a negative classes or the positive classes. So this is how it works. So we'll have a two kind of feed forward and the backward propagations. During the feed forward network, the hidden layers will have a set of weights basically. Maybe I'll come to that detailedly. We'll have a weight value which will get initialized randomly, and then based on the loss or the error value, we'll try to do a backward propagations to optimize this error. That we'll call it an epochs or the iterations. Okay. So these are how it going to work in terms of deep learning architectures. And let's assume you have some business problem or a use case which you want to come up with the solutions of a deep learning or a computer vision based solutions. Considering I have a problem statements which I wanted to, which is basically whether the person is wearing a face mask. Okay, so this is one of the business problem which you want to build a solutions with respect to deep learning problem statements. Then the next thing is to data acquisitions or the data collections part. So here, when I say a person wearing a face mask, like maybe a different genders, a different age group, different regions, for example, Asians, or the skin tone might vary, and the different face mask colors. So these are some of the factors we might need to consider when you do a data collections. And the another part is that your data should not be biased towards one single category. Okay, which means unbalanced data might also create a model overfitting scenarios. Unbalanced in the sense, for example, you have a two classes, like a negative scenario and the positive scenario. For example, you might have too many samples for the negative scenario where person is not wearing a face mask. Okay, let's say you got around 10K samples. For the person is not wearing a face mask, but with the person wearing a face mask, you might have only 1,000 to 1K to 2K samples. Okay, in such cases, the model will have a better understanding the knowledge patterns or the maybe your model biased towards the negative scenario than the positive scenario. So you might need to see how you can get a balanced data samples between across different classes in your data sets. So this is one of the factors you might need to consider when you try to build a solutions with respect to deep learning. Okay. The another part is that we need to have there are multiple. You can split your data set into multiple sets. We can talk about train test and the validation set. Some people will talk about out of sample, holdout set. So it depends on the person to person, but majorly we can categorize into a train and test. Okay. Usually we can talk about 80% or 80% of data samples. For example, if you have a 10K samples, including both person wearing a face mask, not wearing a face mask, a 10K sample, you can consider 20%, which means a 2K sample for model benchmarking or a testing purpose. Remaining 8K samples, you can use it for the model training. Okay. The reason for data split, see, once you build your model, you need some unknown sample to validate the trained model, right? So we can't use the same set of sample for model training and testing. So we should have a newer samples or the unseen samples, which you have used for a model training. So we call it the test set. So you can follow different ratio, 80%, 20%, or a 90-10, even 70-30. But what thumb rule says that a larger number of samples has to be used for a model training than the testing. So that is the thumb rule we should follow when you do a data splits. Okay. The next part we talk about the feature engineering. So feature engineering is nothing but like when you have some visual images, right? I told you, I spoke about image will be represented in a matrix representation, which consists of a numerical value, right? All these images are based on the pixel intensity, right? or the numerical value. So all this pixel intensity might change with respect to several conditions. Like if the person rotate on images, the pixel intensity might move to some other pixel coordinate. If the illumination gets changes, for example, if the picture is taken in a proper lighting condition or outdoor environment or indoor environment, the same object pixel intensity might change. If you zoom, so for example, if you are taking an image which is very closer to the camera, the image will be scaled out. If you take a picture which is a larger distance, then the picture will look smaller. And for example, if you consider a CCTV camera which is mounted on the wall or a 30-degree angle, the object might be tilted or rotated. So you will not have the frontal positions of the objects, right? So there are different factors. The pixel intensity is not going to be in statics, which might get changed various scenarios. So what we need to do, we have to instead of giving a raw data to the model, we have to do a feature engineering. In terms of deep learning, these feature engineerings are taken care by the model itself. But in traditional approaches, if you consider an ML-based approaches, we need to do a handcrafted feature engineering. You have to convert your image into an n-dimensional numerical value that represent maybe a color feature, or it may be texture features, or it may be a key point descriptors, or it may be a histogram features. So these are what we call it hand-defined features, handcrafted features, where the developer or user needs to define what feature engineering has to be extracted. One of the limitations with respect to handcrafted features, it is an application dependent. So I can't reuse the same feature engineering patterns for the other application. For example, if I use a color as one of the features to categorize the visual images, I can't use the same color features to distinguish or to identify the face images. So that are application dependent, especially with respect to handcrafted features. Okay. So once you get a feature engineering or the feature pattern, then we pass on to a model training where we can talk about it may be a supervised machine learning approaches, or it may be unsupervised machine learning approaches, or it may be neural networks. Okay. Then the last one will be, once you have a trained model, then we'll have a benchmarking of our model, where we'll talk about confusion matrix or precisions or the recall. It might vary, the metrics might vary problems to problems. So in this scenario, which I've taken a classification problem, which I've given here, the confusion matrix is one of the metrics to measure how your model is performing, and what will be the precision and the recall based on the confusion matrix. We can come up with the precision and the recall. So now let me move on to the what is a deep learning. So basically deep learning, when I say it is a deep learning architectures, where you will have more number of layers which is stacked one after the others. So where we'll give the input images to the deep learning layers, where the first layer might be trying to extract the shape features, or the horizontal line or the vertical lines. We'll call these features are the very basic features, or the low level features. Use these lines or the edges to detect the shape of the small component or the part of the objects, and then pass this, each of these layer output will be passed on to the next layer in the architectures. And then finally, the last layer, what you get as in high level features, we can say the part of the object or the shape of an object, and then it will be passed on to the fully connected layer or the hidden layers. And then finally, we'll try to predict an output. So we'll try to see what is going to happen on each of these square boxes. I'll talk about what is going to happen inside these layers. Okay. So the neural networks, the base for the neural networks will be our, like it was derived from our human brain system, where we'll say there will be a node or the neurons which receive the n number of input connections, and it does some computations. Basically, we'll do a dot product between the input vector and the weight vector, and then the dot product summed up value will be put onto this node value. And this node value will be acting as an input to the next layer in the network. Okay. So as I told you, like in deep learning, we'll have an input layer and the hidden layers and the output layer. I spoke about how do I define the number of nodes for the input layer. If it is going to be an images, then each node value will be the pixel intensity, and the output layer will be based on the what kind of classifications problem. But in terms of hidden layers, we need to come up with the hyperparameters where we have to initially you can create 2 hidden layers with some number of nodes for each of this layer, and then you can do a benchmarking on the test set and the train set accuracy, and then you can further fine tune those parameters. When I talked about each node receives some input connections, right? For example, here the node value may be the pixel intensity value. It not alone carries the node value to the next layer in the network. We'll also assign a weight value. So this weight value, we'll try to do a model training. So initially these weight values are get initialized with respect to a random initialization, or you can use a Gaussian distributions or some kind of normal distribution. So you can use some kind of a distributions to initialize this weight value. Each of these distributions has some range of values to initialize this weight value. For example, this blue color node receives 2 input connections. So where we do a dot product summed up value of this 2 node value, and the summed up value will be put onto an activation function. Especially the neural networks are used for like to get a nonlinearity. So to get a nonlinearity into the neural networks, we'll try to apply the activation function to the neural networks. So there are several activation functions. So I spoke about hidden layers and the output layers. But the input layer will not do any computations on the input layer, just giving a node value to the next layer in the network. So for the hidden layer, we'll be using a ReLU activation function, most of the scenarios. And output layer will be using a sigmoid and softmax. Sigmoid will be applied for the binary classification, and TANH, we can use it for the hidden layers. But in terms of computation and the accuracy wise, there will be a lot of exponential functions with respect to a TANH, and the range of values between -1 to 1 +1 for the TANH, and the ReLU will be the output value of 0 to 1, and the sigmoid value will be 0 to 1. So there are other activation functions as well. So we have a parametric ReLU, leaky ReLU, and then ELU. So there are other activation functions as well, which I'm not going to focus too detail on this. So what is going to happen in the neural network hidden layers? For example, here I have a smaller neural network architectures, hidden layer with input layer with 3 nodes, 3 values, N1 and N2 and N3. N4 hidden layer 1 with 2 nodes, and output layer with 1 nodes. Okay, assume it's going to be a binary classification. So what is going to happen with respect to neural network? Each layer will be connected from I to I+1. For example, I have a 3 nodes which is connected to the both N4 and the N5 nodes. Okay, so the total number of connections for the hidden layer will be number of nodes into hidden layer into the previous layer, which is the 3. So there will be a 6 connection. N4 will receive a 3 input connection, and N5 is also receives 3 input connections. Okay, but what is going to make a difference here? The N1, the N4 will receive a different set of weight value, and the N5 will receive a different set of weight value. For example, N1 into W14 plus N2 into W24, N3 into W34. So you will do a dot product between each of the input node value along with the respective weights. Okay, these weight values will be initialized with respect to a random initialization. We'll try to learn this weight value through a back propagations based on the error or the loss value. Okay, so similarly, we'll try to compute the N5 node value, where we can talk about N1 into W15, N2 into W25, and N3 into W35. So once you will get the dot product summed up value, that will be passed on to an activation function. So here the f of value represents an activation function. The activation function output will be assigned to the particular node. Okay, so once you got the node value for N4 and N5, then this will be acting as an input to the next layer, which is an output layer with the node value of N6. Okay, so now I'll be able to compute the N6 value, N4 into W46, N5 into W56. where you will get the dot product sum the value and the activation functions output. Okay, so this will be, let's assume this will be a predicted value of your model. So whatever input data we have given, there will be an actual value will be there, which we'll call it the ground truth or the label value. Let's assume that will be an y. So you will have an error value. That error has to be 0, but initially for the first epoch, the error value will not be 0, it will be very high. Then we need to optimize this error by doing an back propagations with respect to one gradient descent weight optimization take minima. Then you can do a couple of iterations at the epoch to optimize this error value. I'll pause it here. Any questions? Maybe let me answer. We need to take an image data set. Okay. See, if it's going to be there are two things are there. Whether you are going to use a plain deep neural network or a CNN architectures. If it is going to be in CNN architectures, then we'll have a few more layers. We'll talk about a convolution layer and a max pooling layer, and then we'll have a fully connected layer or the hidden layers. But if it is going to be in plain deep neural network, either you can have a 3 to 4 layers in a network. Okay. If it is going to be in CNN based deep learning architectures, then it may be even people ResNet architectures, which comes with the 150 to 50 layers. See the depth of the layers, what kind of GPU machines you are using to train your model, and how many data samples you have. So if you're going to increase the depth of the layer, then the amount of time is going to take for model training is also going to increase. So it's not alone the factor of increasing the layer, and the volumes of samples and the hardware oscillations to train your models. Okay. Mission vision, we can talk about video analytics as well. So I'm not going to talk about the we can also say as a computer vision. So video analytics, trying to identify some abnormality when someone is in a video. We can also perform a video classification. That is also kind of a problems we can talk about with respect to machine vision. It depends on what kind of industry applications, whether it's automotive industry or a medical industry, or it may be no finance industry. So it varies with respect to industry to industry. So maybe I'll move on to the CNN based model. Then I'll jump to the hands on how to create a deep learning based architectures. Then probably I'll pick a few more questions. Okay. So I just showed you a simple deep neural network where we can have an input layer and the few set of hidden layers, and followed by an output layer. Right? When you talk about a plain deep neural network. The plain deep neural network does not do any feature engineering. Just it is trying to perform a classification alone. One of the beauty of CNN based architecture which can perform both feature engineering as well as the classification. So in traditional handcrafted feature engineering method, you should have a separate block or a stage to do a feature engineering. Taken care, feature engineering and classification will be put together a single architecture or a single block. But in traditional ways are the approaches where you need to have a separately for the feature engineering part. Let's to show you a simple sample architectures for the CNN. So we'll have a layer called as a convolution layer, and then pooling layer, and then we'll have a hidden layers and the output layer. The right side part, which is already taken care in the normal deep learning architectures or the neural networks. But the new things which we are going to add onto the CNN architectures are the convolution layer. Okay. What is going to happen with respect to convolution? Convolution is not a new term. We have used in traditional image processing operations. For example, if I want to detect the edges, okay, so we use some kind of a Sobel kernel or the Laplacian kernel. You will have a smaller matrix where you will try to slide that smaller matrix to get a feature patterns of the edges, okay, or the corners or the shape of an images, okay. But in traditional approaches, all this filter value or the kernel values are predefined. But in terms of deep learning based approaches, we are not going to have a defined kernel, but this will be learned when you do a model training. Okay. So we'll not have only one feature in a single layer. For example, if I say, so this, I can say this particular layer will be a one convolution layer. In a single convolution layer, you'll have a n number of filters. Okay. For example, here I have a 5 different filters. Each filter is going to produce one set of features. So you'll have 5 different features. One square map represent the one feature map. So in depth will be a number of feature map. So you'll have a n number of feature map, which is going to be passed on to the pooling layer. Or you can also have another convolution layer. We'll have a multiple convolution layer max pooling combinations. Okay, so in this case, I have a convolution max pooling, convolution and max pooling, and convolution and max pooling. One of the beauty having a consecutive convolution and max pooling layer, where you try to have a no high dimensional feature. For example, the first convolution might be trying to extract the like different parts, for example, eyes and the ears and different parts of the cat. And then you are trying to combine that feature at the last, so where you will try to get the parts of an object or the shape of an object. Okay, so we'll try to have a multiple combination of such a convolution and the max pooling layer. I'll show you on one of the example what is going to happen with respect to an image convolution. So let me move to a URL. So we have an image here. The same image is represented in a matrix representation. And then what I'm going to do here, so I told you we'll have a smaller matrix. Okay, so this is a smaller matrix which is going to detect the edges in the images, the sharpen filters. You can talk about different image processing kernels here, Sobel kernel, or the if it is an identity, it is the same matrices, but I'm going to do the Sobel kernel. So this will be the filter value. So what is going to happen here? You'll have this 3x3 or the 5x5 matrix. This kernel will be a smaller dimension, which will be an odd size, 3x3 or a 5x5. You will try to fit this 3x3 or a 5x5 kernel in each of the pixel intensity value. When you fit this kernel, you will see a pixel intensity value in a square boxes, and below after you will see a kernel value. So you will have this 9 pixel value and the 9 kernel value. This dot product summed up value will be put onto the output matrix, or we'll call it the feature matrix. Okay, so whatever you see on the right side, that will be a feature map. So whenever you try to slide this kernel on each of the pixel coordinate, you will see a 9 pixel value and the 9 kernel value. This will be a dot product summed up value, which will be put onto the you will have the same dimension as an output matrix. That will be, for example, here, I'll show you one live examples here. Okay. So first let me show you an original images of this. So now this is the original image. So I'm going to do a Sobel kernel. So this will be the Sobel kernel. After applying the Sobel kernel to the original images, the beauty of the convolution layer will be, it will try to scan the feature patterns. For example, here it is trying to extract the gradients or the shape. It ignored the background images, the structural patterns of the images it is trying to extract. So that is the beauty of the image convolution layer basically. So I showed you with one kernel how we are trying to slide this kernel across the each and every XY coordinate in the images. Let me go back to the slides. So I told you we'll have a n number of kernels. So we have a 2 kernel A and B with a dimension of 3x3. So when I fit into the kernel, so make sure you fit the kernel into center of the kernel into each and every XY coordinate. So when you try to fit the kernel, there is a problem of so when you try to fit your kernel for the boundary of your images, right, which will go outside of your pixel coordinate. For example, I'm trying to fit my kernel, center of kernel into I1 pixels. Okay, so this scenario, what happens here, there are few pixel region which resides outside my boundary of my images, right? So in such cases where we'll not be able to do a feature scanning or the feature patterns at the corner of the pixels or the first row, last row, and the first column, last column, we will not be able to do a convolutions at all. So we have another solutions called zero padding, where we'll do a zero padding on the boundary of an images. Then we'll try to do a image convolution with zero padding and without zero padding. So we have a logic. So assuming we are going to fit into I6 pixel, so you'll have a I1 into A1 and I2 into A2. So 9 pixel value and the 9 kernel value. And then the dot product summed up value will be put onto output feature matrix. So there are two feature matrix, considering there are two different kernels. Okay. So I spoke about how do I solve extracting the feature patterns on the corner of the pixels as well. So we go with the zero padding. So when you do a zero padding, so only consider non-zero pixel value alone and do a dot product, and that will be put onto output feature map. To show you one simple example here, let's assume, so I have a smaller matrix where I'm trying to slide this 3x3 kernel, sliding this kernel on each and every pixel coordinate from the left to right till I reach the last pixels in the images. Okay. So the red color ones are the kernel value and the black ones are the pixel intensity. So after you do a dot product summed up value, the one you see as a convolved feature value, which will be a output feature map. So we have another layer called as a max pooling layer in CNN. So when you do a feature engineering with respect to convolution layer, where you will get a multiple feature map at a single layer, okay, then the feature dimension is going to increase. So how do I reduce the number of feature dimension? Okay. So the pooling layer will be applied next to the convolution layer. We cannot insert, or we can't have convolution layer like max pooling layer as a first layer. So it's supposed to be a max pooling layer after the convolution layer. So we have two kind of pooling layer. We can talk about a max pooling layer and the average pooling layer, but it doesn't do any feature engineering. Especially convolution layer helps in extracting the feature pattern. But in terms of max pooling layer and the average pooling layer, it is trying to reduce the feature dimension in terms of spatial dimension. It will try to reduce the height and width of each feature map, but the number of depth will not change. The number of feature map will not change. And independently, each feature map, we are trying to apply the pooling layer. Okay. So what is going to happen in the max pooling layer? Let's say this matrix is the one of the feature map here. So I have a 2x2 as a kernel for the max pooling layer. When I say 2x2, there will be 4 pixel value or the 4 feature map. Within this 4 feature map, which one is having an higher value? That will be a output value. So, and then what is going to happen here? Then you try to apply the kernel without overlapping. So the first region I have applied the kernel, and the second region which I'm applying without overlapping. But in terms of convolution layer, when you slide this kernel, we'll try to do a overlapping way. But in terms of max pooling way, will not. Most recommended approaches will be without overlapping when you slide your kernels. Okay. So within these 4 pixels, we'll have a maximum value, and similarly, you will come back with the slide value of 2. Then the next regions will be this particular region, and try to find which one is having a maximum pixel intensity or the feature value. So, so usually what will happen after you completed the pooling operation, the feature dimension usually will get reduced by the half of the dimensions. So the input feature map will be a 4x4, which got reduced into 2x2. The difference here between the average pooling and the max pooling, in average pooling, we'll take a mean value, but in max pooling, which one is within the kernel or the filter, which one is having a maximum value. So we'll try to do a pixel test or the try to find out which one is the maximum pixel intensity value within the kernel or the filter with respect to a pooling operation. But in terms of convolution operation, we try to do we'll have a kernel value, filter value, and the pixel value. You will do a dot product between kernel or the pixel value. But here you'll do a pixel test within the input feature value. So let me move on to the Colab hands-on session. So quickly, I'll walk you through the the notebook file. I'm sharing the URL, so you can use this URL later on. So one of the advantages of Google Colab, just I'll give a highlight about the Google Colab. So it is a pre-installed all the libraries, for example, TensorFlow, Keras, OpenCV, all these are pre-set up, and also it will give you a GPU environment to run your notebook file. One of the limitations here, we can't run a larger data samples here, and you can't have a larger depth of the layers as well. So there are certain limitations with respect to Google Colab. There are some pro versions also available, so you can use that. So here, what I'm going to do, I'm going to use the inbuilt dataset from the Keras library, which is the MNIST handwritten digit dataset. So, so here I'm trying to use the Keras and TensorFlow library. And I'm trying to import the necessary functions inside the Keras. We have a hidden layers, and then we have a convolution and max pooling layer, and then we have a MNIST dataset. So, and the number of objects here, I'm going to perform a multi-classifications problem. And then I'm going to define what will be the height and width of the images. So the image dimensions will be going to be a 28 cross 28 into 1. There will be 60,000 data samples for the model training and 10,000 data samples for the model testing. And each image dimensions will be a 28 cross 28 into 1. So 28 will be height and width, and 1 represents it's a grayscale images. Okay. And here, what I'm trying to do, when you feed your data samples image data set into a deep learning architectures, better to normalize the pixel intensity value. So the pixel intensity values range between 0 to 255. But here I'm trying to normalize the pixel values into 0 to 1. Okay, and then what we are trying to do, so we'll have a target variable or the ground truth value, which I'm trying to convert the target values into one-not encoding representation or the binary representation. So we have a digit, the ground truth value between 0 to 9. So which we are trying to represent in a 10-bit binary representation, since we have a 10 different classes. So this particular digit will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, this particular digit ground truth value will be 6. 6 will be represented in a 10-bit representation. From this 10-bit representation, any one position will be a 1. The remaining all other positions will be a 0. So all the ground truth value will be converted into one-not encoding vectors. So you can also talk about period similar functionality we are trying to do for the ground truth value for all your training data samples. Okay. So now what I'm going to do, I'm trying to create a sample CNN architectures to perform a handwritten digit classification. So first thing, you need to create a object with the sequential. So we are going to add each of these layer to the object called model. So the first layer, which I'm trying to add a convolution layer. How many filters we are going to have? I told you there will be a multiple feature map. So how many feature map you need? That will be a number of filters. What will be the filter size? So I showed you a sample kernel with the dimension of 3 cross 3, right? So this will be a sample kernel. So we can also have a 5 cross 5 as a kernel size. So we need to define what type of kernel dimension we need to have, and what will be the activation function. So whether you need to have a ReLU activation function or a TANH activation function. So mostly for the hidden layer and the convolution layer, we'll be using a ReLU activation function. And here the next layer, which I'm also creating a convolution layer with 64 different filters. But for the first convolution layer, the input dimensions will be a 28 cross 28 into 1. For the second convolution layer, the output, whatever feature map output we'll get from the first convolution layer, that will be acting as an input to the next layer. So for the second convolution layer, I'm going to use a 64 different filters, and filter size will be 3x3. Then I'm trying to have a pooling layer. The filter size for the pooling layer will be a 2x2. Before we feed into the hidden layers, we need to reshape the max pooling output into one-dimensional vector, which will be flattened into one-dimensional vector. Then it will be feed into the 128 hidden nodes in the hidden layers. And then the last layer, which I'm creating an output layer with the number of classes. So in this case, it's going to be a multi-classifications. So I'll have a digits between 0 to 9. So number of categories will be a 10. So for the output layer alone, we have two kind of activation functions for the classification: sigmoid and softmax. If it is going to be in multi-classifications, we'll be using a softmax activation function. If it is going to be in binary classifications, we'll use a sigmoid activation function. So we have created a sample CNN architectures. And then if you put a model.summary function, so when you create a layers, you have to use a model.add each of the layers, layer we are trying to create. And then if you put a model.summary, which will give you what will be the output shape from each of the features. Okay. For the first convolution layer, input will be 28x28 into 1. After you do a convolution layer with 3x3 with 32 different filters, if you apply one 3x3, you will get a 26x26. There are 32 different filters. So the depth is going to be 32. So you will get a 32 feature map with the dimension of 26x26 with the square. So the depth will be a 32. And the next convolution layer will be again 64 different filters with the dimension of 3x3. So you will get a 64 different feature map. After you do a convolution, it will be a 24x24. So similarly, you'll have a max pooling layer, which will reduce your feature map height and width of your feature map, but the depth will not change. So usually, if you use a 2x2 as a kernel and the style value of 2, it will reduce half of your feature dimension, which is the height and width. The depth remains same. After you flatten, then it will comes to a hidden layer 1 and the output layer nodes. So now comes to the backward propagation. So I spoke about model feed forward and backward propagation. So when you do a backward propagation, so what will be the loss mechanism? So usually we use a cross entropy loss for the classification problem. If you go for regressions or the predictive analysis, you will go for a RMSE or the mean square error. And here the weight optimization techniques, we call it an optimizer. We'll be using an Adam optimizer, which is a gradient descent, and metrics I need in terms of accuracy. Okay. So now I'm going to feed in all my training data samples. This will be the pixel intensity value, and this will be the ground truth, and what will be the batch size. So what is the purpose of batch here? In this case, I have a larger sample, which is a 60K, around 60 to 70K sample. I can't do a feed forward for all the data samples and then do a backward propagations. Okay, your RAM will get crashed. So usually, what will happen? We'll segment our data samples in a batch wise. Let's say I'm going to take a first 50 samples, do a feed forward and backward propagation, then take a second 50 samples. So we'll segment our data samples in a batch mode, and then epochs will be like how many times you want to do a feed forward and backward propagation. So this is also one of the hyperparameters. Usually what will happen, so we can set this epoch to a larger epoch, then we can have a early stopping condition. So there are early stopping condition, which will monitor your validation loss or your training loss or validation accuracy. Then if your validation accuracy or the training accuracy or the validation loss, it's not going to be changed for a continuous 10 epochs, then you can terminate your model training. So there are a lot of things are there with respect to early stopping and the model checkpoint. So even you can save your trained model weights when there is a model improvements between previous epoch and the current epoch. So I'm just starting the model training, that I have given the training data and the training ground truth value. And then each and every epoch, after it completes the model training, we are also feeding in the test data samples to validate how my model behaves between the training loss and the validation loss and the So you will see there will be a 4 value: training loss and the training accuracy, validation loss, and the validation accuracy. So this I have been running it for 10 epochs, but this can be run for like 100 epochs or the 1000 epochs as well. But I told you, like, we can have a monitoring checkpoints based on the early stopping conditions as well. So once your model training get completed, you can also validate what will be your accuracy score for your test data as well. So and also what you can also do, I'll show you one more notebook file. You can also save your trained model weight in a HPy file, which I wanted to show you. Let me show you that as well. So once your model training get completed, you have a model.save functionality. You can export your trained model into an HPy file. So when you move your code to a productions, right, only this HPy file alone it's sufficient. So you need not to retrain your model again and again. So what you can do, you can load the trained model HPy file directly. You can do a testing or the inferencing alone based on the trained model. So not necessary to do a model training again. So once you are convinced with your validation loss and the training loss and the all the metrics, then you can save your model in a HPy file or a PB file or HPy file. And then you can have a inferencing code where you can load this HPy file and then make predictions alone. Not necessarily you need to do a model training at the production environment. So I'm pretty much done. So maybe I can spend another couple of minutes for the question and answer. So maybe let me go through the list of questions posted on the chat. See, that is what I told you. We have an early stopping conditions. Okay, so you can set the early stop. We have a functionality called as an early stopping condition. You can set the patience. Okay, we have a parameter called as an patience, which will say how many epochs I need to monitor whether the loss is not reducing or accuracy is not improving. Based on that, you can terminate your model training. So we don't have any statistical way. This will be a number of epochs for your business problem. So we don't have anything to prove in mathematically to say a number of epochs or how many depth of layers and what will be the number of nodes for the hidden layers. So that those things will be in hyperparameter tuning. So you have to spend your amount of time on the hyperparameter tuning. Let me share my Git. So a couple of repositories are there. Maybe you can go through my Git. So I'll be sharing my Git repositories here. So I've shared my Git repository as well. So let me see. Usually we use a Python and like you can use a Python-based library like a TensorFlow and Keras to create a deep learning architectures. And you can also use a good amount of libraries, OpenCV and Matplotlib to visualize your images. And you can also use a scikit-learn libraries as well. So someone has talked about early stopping. Let me show you a sample Git repository which you can go through for the early stopping as well. So I think I'll pick that later on. So I need to find out that particular repo. So I'll take some time. See, in video classification, so we need to use a combination of CNN and RNN as well. So you can't use CNN alone. If you are going to use a CNN alone for the video classification, you have to do an individual frame. We also have a 3D CNN, 3D convolutional neural network, or you need to use a combination of CNN plus RNN combinations. Okay. Does segmentation method improve the performance of deep learning algorithm? What is meant by segmentation here? Maybe can you a little bit elaborate? To perform optimization to the deep learning model, do you pre-process before predicting the data? See, the pre-processing, what usually we do, you can do a normalizations on the images. You can do like a converting into 0 to 1. So that will be the one of the pre-processing we'll try to do. Or you can also try to do a like a super resolution. For example, if you have a low resolution images, try to improvise the quality of your images, then try to pass on your model. So which might also improve your model performance. How to do a performance optimization? So see, there are several factors on model optimizations. One will be like you try to use the transfer learning, pre-trained models, try to see whether your business problem has been already solved with any of the deep learning model. You can find out ImageNet pre-trained model weight or a Coco dataset pre-trained model weight. There are plenty of open source pre-trained models are available. Just try to reuse the pre-trained model weights and then customize only the few layers. So that way you can get a better performance in terms of deep learning models. Maybe a few more questions, I'll pick it up. Segmentation, you mean a semantic segmentation or instance segmentation? So we have an instance segmentation and semantic segmentation. Probably you can refer SegNet and the UNet architecture. So even I have done a couple of repository with respect to segmentation. You can also go through the segmentation as well. So I've done it for the SegNet based deep learning architectures for the road scenario. So I haven't done specific to the medical images, but I have worked on a semantic segmentation like a UNet architectures and the SegNet architecture. So probably you can go through a couple of deep learning architectures for the same semantic segmentation. Object size, see, it varies. So if you are going to use any pre-trained model weights, then your image has to be resized to the respective dimension. If you are going to create a custom deep learning architectures, then you can define what will be the image dimension. So if it is going to be a pre-trained model, then your data has to be resized to whatever the architecture which was created basically. So is that my screen is not visible? People who are attending here from the Zoom, still that problem persists. I don't know. So I'll be sharing the PDF versions of my whatever slides I used. Maybe you can touch base with the organizers. See, model wise, so I'll show you one URL, so which might also like helpful. I think we are already the timing. So there are a couple of pre-trained models are available. So initially, as a base model, what you can do, so you can go through this website, so which has the couple of pre-trained models, okay, where it talks about VGG, ResNet, Inception, where it talks about what will be the performance or what will be the model size. Depends on what kind of hardware you are going to deploy your model. So you can use any of this pre-trained model to apply to your custom data set. So let me. Thank you. Thanks, guys, attending late evening as well. Thank you. Thanks.